Hello everyone, my name is Neha and this is the first lecture on electronic circuits. In this lecture, we are going to learn field effect transistors. And these are the topics we are going to cover in this chapter. We will learn about JFETs and their characteristics. We will learn about JFET biasing techniques, JFET amplifiers, MOSFETs and their characteristics, MOSFET biasing techniques, and handling MOSFETs. So in this particular lecture, we will be focusing on JFETs and their characteristics. So let's get started. So JFET is basically formed from FETs, which are field effect transistors, and field effect transistors, they are unipolar device that depends on only one type of charge carriers. Either they can be electrons or holes. And these field effect transistors, they are basically of two types. First is your JFET, which is also known as junction field effect transistors, and another one is your MOSFET, which is called, which the name is metal oxide semiconductor field effect transistor. So these two types of field effect transistor, which is your JFET and MOSFET. These two we are going to study in this particular chapter. So this JFET and MOSFET, they are further divided into different categories. Let's first focus on junction field effect transistor. And if we look into junction field effect transistor, then this is divided into two types. First is called your N-channel JFET, and another one is your P-channel JFET. And these JFETs, they have four leads. First is called your drain, and then the second one is your source, and there are two gates. So we are going to see the construction of N-channel JFET in the next slide. And the area between the source and the drain terminals is called your channel. Because N-type semiconductor material is used for the channel, the device is called N-channel JFET. And if you use P-type material semiconductor for a channel, then that will be called your P-channel JFET. And these channel embedded on each side of the N channel are the two smaller P-type regions called gates. So in case of N-channel JFET, you have two small P-type regions connected on either side, which are called your gates. So always remember, if you are using or if you have N-channel JFET, then those gates, the two gates on opposite sides, are of P-type. Whereas if you are using P-channel JFET, then those two gates are going to be your N-type. Now we're gonna see the construction of JFET. But before I jump into the construction of JFET, I would compare these field effect transistors with the BJTs, which are your bipolar junction transistors, and which you have studied in the previous classes. So we're going to do a small comparison and see how they both are different from each other before discussing the construction. So BJT, you know that is your bipolar junction transistor, and which is a three-terminal device. And in BJT, you have base, you have collector, and the emitter. Whereas if you see the FET, which is your field effect transistor, it has basically three terminals: drain, source, and gate. And there are two gates. As you can see in this particular construction, gate 1 and gate 2, but they both are connected together, and that's why they are called a single gate. So it also has a three terminals. But the difference between these two is that BJT is a current control device, whereas field effect transistor is your voltage control device. What does that mean? Which means that your BJT depends upon the output current of the BJT depends upon the input current. Whereas in the field effect transistor, the output current is dependent upon the input voltage. And in BJT, it depends, since it is a bipolar device, it is dependent upon both types of carriers, your electrons as well as your holes, whereas in FETs it depends either on holes or on electrons. So that was a brief comparison between the BJT and the JFETs. Now we are going to see the construction of JFET, and as you can see on the screen, we have two types of JFETs: N-channel JFET and the P-channel JFET. If we look closely on the N-channel JFET, you will see that there is a drain on the top and source at the bottom, and then you have these two gates, and these two gates, gate 1 and gate 2, are connected to the P-type region, and in the between, at the center, you see the N channel. So if you have a construction like this, then that will be called your N channel JFET. On the other hand, we have this P channel JFET, and in this we have a drain terminal on the top, source at the bottom, and these two gates. And if you notice that these two gates are connected to the N-type region, and at the center we have P channel, which is basically sandwiched between these two region. And if you have a construction like this, then that will be called your P channel, because at the center you see this is the P channel, whereas in N channel JFET you have the N channel. So this is the construction of JFET, and now we are going to move on to the next slide. So this particular slide shows the symbol for N-channel JFET and P-channel JFET. So this particular figure where you see the gate direction is towards this gate terminal. And then if you have something like this symbol, then that is called your N channel. And if you have the direction going away from the gate, then that is called your P channel JFET. So this is your N channel JFET, and this is your P channel JFET symbol. Now next is the current flow we are going to see in an N channel JFET, where we have P types gates. Right now these gates are disconnected, and there is a connection we can see between the drain and the source, and this is the positive VDD voltage has been applied. So here the current which is flowing in this circuit depends upon the two factors. The value of the drain source voltage, which means the voltage between the drain and the source, that is called your VDS, and this VDD you are applying, and the drain source resistance, which is designated by RDS, and that drain source resistance basically appear in between the drain and the source. Okay, so the amount of drain current which is flowing through this channel depends upon the potential between the drain and the source, which is your VDS, and also the resistance, drain source resistance, RDS, formed between these two terminals. Now next we have these two circuits, and in these two circuits they basically, first of all, they are N-channel JFET, because you can see the channel is your N, and on the opposite side we have the P-type gate, and then we have a supply VDD connected of 15 volts, and the same in this circuit. And what else is similar? So we have this circuitry is similar in these two circuit, and these two gates are connected. Gate 1 and gate 2 are connected. Same here, the gate 2 are connected, and then source is grounded here. Now the difference between these two circuits is that in this circuit we are providing the negative voltage, gate to source voltage, which is called your VGS, negative gate to sources, whereas there is no negative gate to source voltage. Instead we can say your VGS is basically 0, or you can say your VGG, your gate to gate voltage, this is your 0 because it is grounded. Okay, so that's your first case when your VGS, gate to source voltage, is grounded, and this is the second case when your VGS is negative. And we are going to see what will be the impact of these two different types of voltages on the N channel JFET. So if you notice, like if your drain to source voltage is equals to VDD, which is 15 volts, which means it is positive voltage, and because of this the electrons will drift towards the drain from the source side. Okay, from this source side, the electrons will drift towards the drain side. And if we talk about the conventional current, which is your ID, drain current, that is going to flow from here. You know that there is a conventional current and there is a natural current. And so the conventional current is going to flow from here, from drain to source, whereas your natural current, which is basically due to electrons, that will flow from your source to drain. Now in this particular case, when VGS is 0 and VDD or your VDS is positive, then what will happen? The width of this depletion layer, you can see here, this depletion layer will increase at the top and it will decrease at the bottom. That is because the positive voltage is applied to your N-type material or N-type channel, and 0 volts is applied to your P-type material. So that is why the width of depletion region will increase at the top and it will decrease at the bottom. Now there is a voltage called your pinch off voltage. So what is that voltage? So on increasing the VDD, when you increase this VDD, which is equals to your VDS, which is drain to source voltage, then you know that width of the depletion region, this depletion region or layer, will increase, and it increases to a level where it appears that the two depletion regions are touching each other. You understand? So when you increase this VDD or VDS to a level that these two regions, they appear to touch each other, and that condition is called your pinch off, and the voltage corresponding to that point is called your pinch off voltage. And pinch off, a word came from a pinch, which means gripping the object, and in reality, if we see these two depletion region, they will never touch each other, but the width is going to be very, very small and very close to each other. And the reason why these two depletion region will never touch each other is that the voltage drop across the resistance here, the resistance which is formed in between the channel, these channel, is basically, here the resistance is going to very small, because you see that the depletion region is going like this channel is making like this. So here you have the stronger voltage, and here you have the stronger voltage, which means less resistance, and here you have less voltage up here. If you measure the voltage across this channel, then here you are going to have stronger voltage, and here small voltage, and this small voltage due to higher resistance. So when the voltage drop across the resistance, you know that it is due to the current ID, and when two depletion region touch each other, then that means that there is no current flowing, which means that ID is equals to 0, and that cannot be possible because there is a drop across the resistance, and the drop across resistance is not 0, and that will be possible only if there is a reverse biased voltage applied through this. And now we have the second case in which we have gate to source voltage which is negative, and we have VDD or the VDS, drain to source voltage, which is positive. So in this case, what happens on increasing the VDS, the width of the depletion region will also increase, similar to this case, which means more at the top. The depletion region, this layer is going to be more at the top and less at the bottom. And after some time, two depletion region, they will appear to touch each other, which means the pinch-off condition will reach, and corresponding voltage drain to source is called your VDS, is your VP, which means like when the pinch-off condition is reached, then at that time whatever the voltage is called your VP, that is your pinch-off voltage, and that pinch-off voltage is basically the voltage between drain to source. Okay. So in this case, the VP in case 2, in this case, is less compared to VP in this case. So the pinch-off voltage in this case will reach early compared to this, compared to the pinch-off voltage in this particular case. And the reason is that because we are applying the negative voltage through the gate, and due to which the pinch-off condition is reached early in this second case. So you understand the basics in these two circuits is that in this VGS or VGG, gate voltage is 0, and in this case your pinch-off voltage will reach, but these two regions are not going to touch each other because there will be some amount of current flow, which is ID. And this is the second case in which you have applied the negative voltage, but the positive voltage is still there, and in this one also. And in this case, the pinch-off voltage will reach early. Now moving on to the next slide, we have this FET and channel FET, and this is the gate to gate voltage, and this is negative gate voltage is applied, and this is the VDD, a positive voltage is applied between drain to source. And this is the characteristics between ID, which is the drain current, and the VDS, which is the drain to source voltage. And you can see in this particular characteristics, when the VGS is 0 volts, then the maximum drain current is this, and you can see the pinch-off voltage has arrived really late. So in this particular case, is VP is equals to 4 volts, and that is 4 volts when your VGS is equals to 0. And as you provide the negative gate voltage, you can see the pinch-off voltage can be achieved early. So for example, when VGS is negative 1 volts, then your pinch-off voltage is at this position, and when it is further decreased to negative 2 volts, 3 volts, negative 3 volts, and further to negative 4 volts, then your pinch-off voltage is basically decreased, and at this particular position it is somewhere here. So at negative 4 volts, this is called your VGS off, which is the minimum VGS, and this is IDSS is called your maximum drain voltage. And then this region, the region between when VGS is equals to 0 volts and when the pinch-off voltage is achieved. So on the left hand side towards this, on this side, this region is called your ohmic region, when VGS is equals to 0 and depletion layer is very small. JFET acts like a voltage controlled resistor. And at the bottom here is basically called your cutoff region, which has not been shown here, but that is called your cutoff region, where VGS is VGS, gate to source voltage, is sufficient to cause the JFET to act as an open circuit, as channel resistance RDS increases to the maximum value. And so here it will act as an open circuit, and here this is called your saturation region, and in the saturation region JFET becomes as a good conductor and is controlled by gate source voltage, while drain source voltage has little or no effect. And then further, this it has not been shown in this characteristic, but this graph goes like this, and that region is called your this goes above like this. So that region is called your breakdown region, in which your VDS is very high, drain to source voltage is high enough to cause your JFET resistance channel to break down and pass uncontrolled maximum current. So this was the characteristics of JFET, and that is the end of the lecture. Thank you so much for watching.